Dobro, možemo početi. Ovo ću samo kratko hrvatski, zato jer je neka tehnička stvar. Znači, s obzirom da ako neko ispadne i vrati se, ide se vraćati, ja ga ne vidim, a vi ćete vjerovatno vidjeti da se želi neko vratiti, onda nekako me alarmirajte da ga uključim nazad u ovaj sastanak. Okay, so next topic today is actually data analysis. I hope that you're able to see my presentation. Yes. And that you can hear me as well. So we will start. As I said yesterday, data analysis is often overemphasized as a part of research education, scientific education in our country and in the whole territory. There are some reasonable explanations for such status overemphasizing of the data analysis. Basically, data analysis is something which is not our students and our colleagues are not familiar with. So in some cases, it is difficult to understand and complicated and so on. But by all means, this part of the research and this part of the overall scientific work is not the most important. Simply because you can always find someone to help you with. It is good to know how to process the data, how to do data analysis. But as I said, there is always a chance to find someone who will help you with it. And currently, it's easy even to learn a lot about data analysis. There are numerous tutorials and webinars about data analysis. And simply because of that, I think that data analysis and the problem of statistical analysis should be covered in scientific education, but basically not so tremendously as it was before, as the practice is still in most of the universities. I'll give you one simple example. Currently, one of my former students, our assistant, is doing data analysis I have never learned in my life. And I like to consider myself as good in data analysis and statistical analysis. 1 year ago, throughout the review process, one reviewer asked him to do additional data analysis. I didn't know how to process the data on that way, so he found the webinar, 1 or 2 days of the webinar, and he's an expert in this statistical analysis right now. Probably the only one who is able to process the data throughout this analysis in our country. So basically, it's much easier than it was before, when you relied on someone's expertise and you should listen the lessons and classes and pass the exam and everything else. Today it's much easier. So we will cover data analysis, but almost certainly not so extensively as it is usual in scientific education in the country so far. So something about the previous steps, the steps which precede data analysis. After collecting and preparing the data, you have to do the research process and you have to do the data analysis. It is often misunderstood that data itself will provide someone the answer to the research question, which is not actually is not absolutely right. It's not absolutely wrong. Of course, without data, you will not have the answer, but data itself are not exclusively and only necessary for providing the answer to your research questions. So data should be analyzed, and even more should be interpreted. Because if you can recall the previous lessons, you have to answer your research question, your questions. So you have to analyze data, but as well you have to interpret correctly your findings. And collectively, and in the most common words, and it's not very common, but relatively usual wording is that this process is called quantitative analysis. So if you analyze some data, some collected data, which are statistically processed, and then you interpret it, then you are doing quantitative analysis. Try to remember this term, because later on we will introduce another term for which is also used for interpretation. Of course, probably the most important part is in data analysis is choosing the right statistics. When you want to do, and this is the part I believe each scientist must know sufficiently. So you have to be able, you must be able to understand the background of your data and anticipate the possible interpretation, and accordingly you have to choose the right statistics. In doing so, you have to ask yourself some questions, and it will probably allow you to objectively and sufficiently, and I believe objectively choose the statistics you will use in your research. So here are some questions you have to ask yourself. What exactly do I need to find from this data to answer my research question? I have to highlight one word here. What exactly do I need to find, and not what exactly do I want to find? So basically, it is important to anticipate what do you need to find to answer the research question. If you target the wording want, then you will target probably the wrong statistics. So the need is the background. After answering this question, then you have to move forward and ask yourself another question. What statistical test will give me this information? Again, this need, not want. And finally, what do the results from this statistical test mean? As I said previously, you have to know something about it. And the most important part is this first question. I will underline it. Simply because if you are able to put this question objectively and answer this question objectively, then you can find someone to help you with these two topics, with these two questions. Okay, it's always better to know how to answer the second and the third question, the answer of the second and the third question, but it's absolute prerequisite of successful investigation is to know the answer on the first one. So what exactly do I need to find from these data? And you can then ask for someone's help if you are not certain, if you are not absolutely positive about the answer on the second and third question. Generally, it's a closed circle. So basically, the importance of this process lies in how such statistics are interpreted and how that interpretation is related to your research objectives. The problem is that you cannot ask someone's help, or at least you cannot ask for statisticians' help. You can ask someone to help you, your mentor or someone like this, to help you with this question, but statistician cannot help you with this question, because consider a statistician as a sort of artificial intelligence. So he or she is still not able to objectively overview your idea. So basically, the first question you have to answer yourself, and then you can ask someone's help, because the important thing is how statistics are interpreted and how it is related to your research objectives. And if you didn't answer your question, the first question, objectively, then you are in a problem and no one can help you. Generally, all statistical analysis can be broadly divided into two separate forms. The first group of statistical analysis are descriptive, and the second group is inferential statistical analysis. The basic idea of the descriptive statistics is to organize your data, meaning that organization of the data is absolutely the first priority of all statistical analysis. Meaning that you cannot put the data on a wrong way, and descriptive statistics will show you if you did it like this. For example, one example of the organization of the data is frequency counts of participation in sport, or calculating the average points scored by game by a particular team. I'll stick to the first example and try to point what happens if you organize data wrongly and how you will see that the organization of the data is not proper. For example, you have a question on sport participation. You have volleyball, basketball, and football. Let me put it this way. So 3 sports: volleyball, basketball, and football. And now you are naming each subject according to the participation in sport. And you will put volleyball, football, basketball, football, basketball, and after some time you will make a mistake and you will not the term basketball, but you will say basketball without a. It seems that it doesn't mean a lot, but actually it is. It's a huge mistake, because the statistical analysis recognizes this mistake in wording as a new entity. So it's not basketball, it's basketball, and it counts it at 4th group. You will not be able to see is there something wrong before you do descriptive statistics and see how many participants are grouped in each of these sports. So you have 20 basketball players, 25 football players, 26, volleyball players, and 2 basketball players. So you will see that something is wrong, and then you can go back and correct it, and then do this descriptive statistics again in order to clean up your data. It's absolutely crucial, because later analysis will follow this mistake and will include this mistake in this error in analysis, and you will have a wrong numbers later on, which actually stops any meaningful interpretation and do not allow you to do statistical analysis at all. Actually, you will do a statistical analysis, but the results will not be correct. Just a moment, I think I have to do something. Okay. So another example of descriptive statistics is calculating the average points scored by game by a particular team. For example, if you put descriptive statistics for, I don't know, 30 games, and for average number of scored points per game for 30 games, and you put 10 for example, I don't know, handball game altogether, scored goals are 40, 40, 40, 60, 55, 39, so on, and you make a mistake and put 390 instead of 39, so you put 10. In large data sets, you are not able to see what's going on, but if you do descriptive statistics, you will see that minimum is, for example, 20, which is reasonable. I don't know if let's suppose that it's reasonable. Average is 45, okay, this is reasonable as well, but the maximum value is 390, and then you will be aware, okay, then there is some mistake, let's see what's going on, so I can clean up my data metrics and organize the data, sufficiently precise. As I said, the problem is not in data itself, but later statistical analysis, because if you have a mistake at the very beginning of the data set, then you will have, this mistake will accentuate later on in other statistical analysis, and you will have a problem with statistical analysis later on. In some cases, you will not be even aware that you have a problem in data. So for this reason, descriptive statistics are of utmost importance as a form of statistical analysis. The second phase are inferential statistics, which actually allow you to infer relationships or differences. Relationships between variables or differences that exist between two or more variables or sets or whatever. So basically, all inferential statistics can be additionally separated into relationship and difference statistics. So, for example, of the relationship, correlation, to calculate the correlation between experience in sport, I don't know, and ability at a particular sporting task. For example, are those who are more involved in, I don't know, diving, sport of diving, able to do more complex elements or not, so something like that. Or the second example, differences example is gender differences in sport preferences. Are males more oriented towards some sports and females towards some other sport in some country or so on. So basically, descriptive statistics allows you to organize your data, and inferential statistics allow you to infer relationships or differences that exist between two or more variables. Please mute yourself, someone has a microphone. So let's start with descriptive statistics more in details. So generally, descriptive statistics include two types of measures. First, measures of central tendency, and the second are measures of variability. Measures of central tendency, such as arithmetic mean or mode or median, are generally numbers, values that describe a particular characteristics of a test or scores. So, for example, if you want to explain briefly the sample of subjects, you will probably say they are 185 centimeters in average. It means the mean of their results on body height is 185 centimeters. It is a very common way of expression, and the measures of central tendency are frequently used, even in common language between us, such as, for example, I don't know, at our faculty, they are not able to do 10 pull-ups. You know what the pull-up is. So when you try to explain that the generations are deteriorating in their physical fitness, we use some measure of central tendency because they are not able. It means that their average is about 10 centimeters. 10 pull-ups, sorry, 10 centimeters. In some cases, you will use mode, and in some cases, mean. Let's see the difference. You all know probably that the mean is the average score of all observational variable, and is calculated as a sum of all scores divided by number of observation. For example, in this case, you will have a mean of 3.38. I don't even know where this example comes from, but it doesn't mean. Možete li ugasiti mikrofon, molim vas? So I don't know where this example comes from. It's not important, but the mean is, as you can see, 338. Example from the sport, actually, I mentioned previously the example from our faculty, but basically there are numerous examples from the sport. I will not waste your time because each one of you will be able to recognize some of the results which are represented by mean, not only in research process, but also in regular life, everyday life.
Ne to, nego imaš, znači, tapetić, imaš sa strane, pišu vamo, znači, jučer si daš prema ovde, on znači si opet izgleda.
So, what is the mode? Mode is the value that appears as the most often. Calculate is very simple. You have to put all numbers, you have to see all numbers and count which one appears most often. For example, in this data set, mode is 1. I know that it would be rather difficult to understand to find the example from the sport right now at once, but maybe someone can find something like that. For example, I don't know, if we will observe some huge competition and the number of exclusions, and the mode is, for example, 7 or something like that. I don't know. Generally, I cannot recall any right now. I cannot recall any example where mode is used in everyday life. And the median is the third measure of central tendency. This is the point that divides the observations which are ordered into equal parts. So value exactly in the middle. So when you have to split one group into two subgroups for the purpose of comparison. So in this case, the mode is 3 or so on. Generally, in statistical analysis in research process, median is the most commonly used, measure of central tendency because it represents the data most objectively represent the data. However, when data are not normally distributed, then in some cases you should report even mode or median to better represent your data. The second set of descriptive statistics are measures of variability. These measures actually indicate a dispersion in a data set. So how data is variable, what's the variability of the data? Meaning that high variability means that values are much less consistent, are not so consistent. And it means that it's harder to make a prediction of central tendency parameter. So let me put it this way. If you have a huge variability of result, then you are less able to predict some average data. If you have a small variability of result, then you are pretty comfortable with guessing where the central tendency tends to be. So basically, this is it. And low variability, better prediction based on sample data. The most commonly used measures are standard deviation, variance, or range. Range, later on, in last couple of years, I see the growing interest in range, especially in sports science, especially in those research articles where authors try to represent some sample of subjects. In these cases, they present the whole range. So it means minimum to maximum results. Because if they actually try to highlight the importance of their data as a model characteristics, then they should also, they try to present the range. Otherwise, people will not understand, is there I don't know, athlete or subject good or bad if range is not presented. So start with standard deviation. Standard deviation generally measures the extent to which scores deviate from the mean. Deviation on the right or on the left side. High standard deviation means that values are generally far from the mean, and low standard deviation values are clustered close to the mean. So they are very close to the mean. If two samples have identical means but differing standard deviation, it actually means that you have, for those with lower standard deviations, lower standard deviations, you will have a more homogeneous sample. In sport, it actually means that they are better, more selected. For example, if we will measure the, let me put it this way, if we will do the research on top level basketball players and find their top level professional basketball players, for example, first division of Croatian league, first division of Croatian competition, you will have a mean of 200 and I don't know 1 as average height. And I suppose that in other countries around, also the mean will be pretty much the same. But the standard deviation will depend on heterogeneity of the subjects. I don't know exactly where is the best basketball in these countries around. So I suppose that, I don't know, for example, in Croatia, we will have a huge dispersion of results than in Serbia. We all know that they have a better basketball, but the lower dispersion, lower standard deviation than in Bosnia and Herzegovina. I hope that we have a better basketball than they do. And pretty much, I don't know what about Slovenia, I'm not certain. But basically, this is what I'm trying to point out. So standard deviation in a normal distribution means that about 68% of all scores of all results are within one standard deviation of the mean. And almost all of the results, 99.7% of all scores are within 3 standard deviations of the mean. Meaning that within plus and minus 3 standard deviations, in normal distributions, you will have all of your subjects. Only some, maybe 1 on 200 participants will be out of these 3 standard deviations. Variance is very much the same, pretty much the same as standard deviation. It's a measure of variability, and it's calculated by taking the average of square deviations from the mean. And variance tells you the degree of spread in your data set. The more spread the data, the larger the variance is in relation to the mean. actually, standard deviation and variance are hardly correlated because they are calculated one from another. Their units only differ, meaning that standard deviation expressed in the same units as the original value. So, for example, in centimeters. And variance is expressed in much larger units, meaning that original values but squared, meaning that differences are only in numbers, in units, and not in meanings. And finally, now we have finally the range. As I mentioned before, its growing popularity in sports science. You will easily understand why is it important. It is the easiest measure of variability to calculate highest minus lowest value, because the range allows everyone to understand, even those who are not familiar with statistics, how the data are dispersed. So if you have a huge range, data are highly dispersed, and if you have a small range, then data are not well dispersed. As I said, these modal characteristics and presentation of the top level results with the aim to present the model characteristics of the data are the most common reason for presenting the range in scientific literature. All of these analysis, descriptive analysis and descriptive data, are actually the part of parametric descriptive statistics, meaning that in cases when you have a normally distributed variables, as previously presented, you are using means, modes, medians, standard deviations, and so on. But when you don't have normally distributed variables, but variables measured on ordinal or on a nominal scale, such as, for example, males, females, it's a variable gender, or sport, volleyball, it's a variable sport, or even, I don't know, good, average, bad, still there is the scale is not sufficiently sensitive, so you have in these cases you have non-parametric descriptive statistics. So these statistics should be used when the data are qualitative. All of these terms I used previously and examples I used previously means that data are qualitative. I know that it seems strange when compared to Croatian language that qualitative means some quality, good, and so on. No, qualitative means that you are not, qualitative data means that you are not able to numerically define the quantity of differences between subjects. So male and female is a qualitative data, but it doesn't mean that males or females are higher in quality. No, it doesn't mean that. Okay. So data qualitative, the distribution is not normal. Of course, if you have a sample of, for example, 100 pupils, you will have probably 50% 50 males and 50 females, and you will have only two columns, one with males and one with females, and it's impossible to be normally distributed. Even in sports, volleyball, handballs, I don't know, because you don't know which one to put first. Distribution is not normal, variances are not homogeneous, and for small sample, and in some cases you should use non-parametric descriptive statistics for small samples, even when you measure normally distributed variables. For example, if you measure height, body height, in some specific sample, for example, I don't know, some rare sports or ultra endurance athletes from Split, I don't know, something like that, then for small sample you will use non-parametric descriptive statistics even for no expected normally distributed variables. For nominal variables, you will use frequency. Nominal means that you have a name of the variable, such as gender, such as type of sport, such as, I don't know, urban rural environment, such as I don't know, northern part of the country, eastern part of the country, southern part of the country, so on. So then you will calculate frequency tables, you will calculate percentages, and you will present it by graphical presentation, such as columns or pies or something like that. And you will use non-parametric descriptive statistics for ordinal, for example, scores, school grades, 1, 2, 3, 4, 5. These are ordinal variables, but they are not normally distributed because scale is too shrinked. You have to have, I don't know, scale of 10, 11, even 12 to calculate descriptive statistics for scores. So for ordinal and quantitative variables, you will use frequency tables, histograms, mode, median, sometimes mean, standard deviation and distribution, and asymmetry. Okay, so this was briefly about descriptive statistics, and now we will move forward to inferential statistics. So let me accentuate once again from the very beginning. The idea of descriptive statistics is to see what's going on with your data and to organize your data. It will allow you to objectively overview, is everything okay, all right with your data, to make some corrections if necessary, to make some amendments, to see if you put some result wrongly, and to find the right way to present your data, to show what are you dealing with to everyone else. But inferential statistics, and very rare, extremely rarely, descriptive statistics are sufficient to present the findings and to find the answer to your research question. Very rarely. In some cases, it is possible. For example, when people tried to cover the aspects of the COVID pandemic in the first phases, they wanted to do only descriptive statistics because it allowed them to see what's going on with these people, and nothing else. In later phases, inferential statistics were done. So inferential statistics, while descriptive statistics summarize the characteristics of a data set, the real answer to your research question comes from inferential statistics, because it allows you to come to conclusions and make predictions based on your data. It's impossible to do it on the basis of descriptive statistics. You are not able to say, are boys taller than girls in the 4th grade of elementary school on the basis of descriptive statistics. Yes, you can see that boys are, for example, in average 140 and girls are 135. I don't know if it's correct, I'm guessing. But still, you are not able to say, yes, this is sufficiently different to say boys are taller than girls. So despite the fact that descriptive statistics gives you the results, you are not able to define the relationship or differences on the basis of descriptive statistics. So you have to calculate some form of inferential statistics. This is the most tricky part of any research, because you have to decide which test suits your research question. There are numerous tests used for almost the same purpose, but you have to decide which test suits your research question mostly. And this is based on your data, because you have to consider whether your data meets the conditions necessary for parametric tests, or you have to do non-parametric tests. So basically, there are two categories of inferential tests. The first group is parametric group of parametric tests, and the second group is group of non-parametric tests. It's not difficult to guess that parametrics are used for parametric data and non-parametric for non-parametric data or qualitative data. And the difference is basically that parametric tests, in some cases named as quantitative tests, these tests use interval or ratio data and assume that data is drawn from a normally distributed population. Meaning that if you have two groups of participants, parametric tests assume that all of them are actually members of the same population, but for some reason they could be different. For example, males and females in body height, they are by all means drawn from the same population of humans, but because of the biological factors, they are different in body height or in body fat, or I don't know what. But basically you have samples drawn from the same population. And because of some reason, we consider them as different in some parameters, but still they are the same population. And the second group are non-parametric tests, which are used when you have ordinal or nominal data, and you do not make assumptions about the characteristics of the sample in terms of its distribution. So you have nominal or ordinal data. Let me repeat it once again. Nominal data means nomen in a Latin name. So nominal data are organized simply by name. Males, females, male, female, or volleyball, basketball, football, handball. So it means nothing but the name, but the group. It doesn't mean any difference in the qualitative or quantitative term. Male, female as well. And nominal data means, ordinal data means order, which means that there is some order in school grades. For example, grade 1, score 1, grade 1, and grade 2 are different. Grade 3 is different than grade 2. But the differences between grades are pretty strict. And there still can be lots of participants, lots of children who are scored by 2 and while being different. In interval data used for a parametric test, this is not the case. You can always calculate, you can always measure the difference, even for people who are 182 in body height. Still, there is someone who is 182.1 and another one is 182.3. So basically this is it. So these are the differences. And we will conclude before the break, short break, tests for analysis of differences. You can use t-test for independent sample, or its non-parametric variance is Mann-Whitney test, t-test for dependent samples, and non-parametric variant is Wilcoxon test, and Wilcoxon, this is partly in Croatia, one-way ANOVA or non-parametric variance Kruskal-Wallis test, ANOVA for repeated measures or non-parametric variant Friedman test. And for analysis of association, you have Pearson's correlation coefficient, Spearman's correlation coefficient as a non-parametric variant, and binary logistic regression with no non-parametric variant, but because this analysis can be used both on parametric and non-parametric data. We will talk about each of these analyses in next 45 minutes, but we will take a break of 5 minutes. So we are continuing in 5 minutes. Okay, thank you. Okay, we can move on. So let's start with analysis of differences. T-test for independent samples. I suppose all of you had a chance to see the results of t-test for independent samples. The basic idea of this statistical analysis is to see are there any differences between mean scores of two different groups. I mean that when you have to calculate the t-test for independent samples, you have to consider the groups as independent for some reason, theoretically independent. As I said, results of body height in boys and girls. For this analysis, you must have one variable which divides groups such as gender, males, females, or boys, girls, but only in two groups, not more than two, not 3 or 4 groups, only 2 groups. Boys, girls, athletes, non-athletes, I don't know, urban, rural, I don't know, swimmers, non-swimmers, and something like that I cannot recall right now. Starters, non-starters in sports and so on. But you must have one variable representing the group, 2 groups, 1 group or 2 groups, and the second variable you intend to analyze whether these groups are different on this variable or not. For example, body height, boys and girls on body height. Are there any differences in body height for 2 groups? I have to quit currently the presentation of PowerPoint in order to show you the idea. So I will do it later on when we cover all of these analyses to show you the differences in approach. But basically, you have to have only one variable presenting the group and the another variable presenting the variable of interest you intend to see are there any differences according to group. It can be used when the data is interval. So you cannot calculate the t-test for independent samples, for example, for if you have 2 grouping variables such as gender, boys and girls, and the second variable preferences towards sport. And then you have football, basketball, volleyball, football. If you have a variable which is not interval, then you cannot calculate t-test. The factor of random assignment is very important. The 2 groups are independent of each other, and the variance in 2 groups should be equal. So it means that actually distribution of results in body height, I'm taking this example as the most common and most convenient, the distribution of the results of body height in boys should be similar as distribution of the results for body height in girls. So despite differences in means, in average values, distribution of results among boys should be similar to distribution of results among girls. So let's find some examples from the sport. For example, I don't know, it's not the example from the sport, but from the physical education, there's differences in body height between boys and girls. But when you have non-parametric tests, when you have non-parametric data in ordinal way for ordinal tests, such as, I don't know, scores, grades in school, 1, 2, 3, 4, 5 in our school, then you use Mann-Whitney test. And when you have when you have to calculate the differences between groups, but in nominal data, as I said previously, boys, girls, preferences towards sports, then you calculate square test. There is one example of usage of t-test in one of our articles, where we actually define the differences between starters. Just a moment, I have to move to this presentation, because otherwise I will not be able to show you. So in this table, just a moment. Just a moment. Share screen 2. Would you please stop? So here you can see the differences. Sorry. We calculate the differences between starters and the non-starters. And with these small asterisks here, we actually presented the t-test differences. So let me put it this way. Let's find something that you will understand. For U13, for young players, you have sprint of 10 meters and of 183 in average, plus minus 0.15, and 2.707 for older, which means that for non-starters, meaning that starters are quicker, they're faster, they're better in sprint of 10 meters than non-starters. Same goes with U15, where some other differences, where same differences are calculated, but as you can see, the only difference is in this test. I will not explain you right now. It's a reactive agility test in football. This is a common example of the calculation of t-test for independent samples. Why independent? Because starters and non-starters in both age groups actually comes from the same population, but this same population still could be different according to this training status, this performance status, starters and non-starters. So this is actually the first example of this t-test. I believe it's pretty simple to understand, and the idea is pretty simple. The second test is t-test for dependent samples. The idea of t-test for dependent samples is to calculate and to establish the possible differences within the same group, but when this group was measured, in cases when this group was measured in different time points. For example, at the beginning or at the end of some period. I don't know, before training process and after training process, or for example, at the beginning of the school year, at the end of the school year, before some treatment or after some treatment, and so on. But still, you are comparing only 2 time points, so prior and late, before and after. The idea of this test is to show are there any difference within the group. So in non-parametric data, you will use Wilcoxon test. And there is one example again from our study where we actually compared the data of football players before and after the COVID illness. So we compared actually their running performances, the running performances they achieved at the game before and after they were infected by COVID. And in this case, we didn't present, as you can see, the results with the asterisk, but here at the end. And as you can see, this P showed that in these two variables, high intensity accelerations and high intensity decelerations, we have found the significant differences, meaning that players were not able to do as much high intensity accelerations and decelerations after the COVID, after they were infected by COVID, they had COVID illness. So the number decreased from 28 to 21 or 38 to 31, and t-test was significant. In other variables, we didn't find the significant differences between within the results of the same subject before and after the COVID illness. I have to repeat, in this case, you have to organize the data in two columns. So these are subjects and their results at the first measurement, and these are the same subjects and their results at the second measurement. Actually, if there is, one, for example, 100, then here he or she will have pretty much something similar, but of course possibly different. Let's say 133. But what is important, you have to put all subjects in each subject in only one line. But the results of the first measurement are in first column, and the results of the second measurement are in second column. This is very common mistake to put the results of subjects in two lines. For example, this is Ante at the first measurement, and then again after 100 and I don't know how many columns, this is Ante at the second measurement. No, this is not correct. You have to organize the data likewise in two columns, and each subject appears only once in one line, but as I said, results are in two columns. Then the statistical analysis will work. I said previously that t-test is basically used only if you have two measurements, t-test for dependent samples, or two groups for t-test for independent samples. But in some cases, you will have three groups. For example, I don't know, volleyball, basketball, and handball players. Or, for example, under average, average, and above average quality. And or you will have three measurements. In cases when you have three groups, you will use one-way analysis of variance. It's very similar in nature to the independent t-test, but as I said previously, independent t-test is calculated for two groups, and ANOVA is calculated for three or more groups. It allows you to certain differences between more than two groups. Just a moment, I have to see, am I sharing the right one? Yes, I am. So it allows you to certain differences between more than two groups. And what is even more important, just a moment, it allows you to do the calculation for, I don't know, not only 3, but 4, 5, 6, and so on groups. The problem is that you will have only one result showing are there or are there not any differences among 3 or 4 groups, but you will not know which group is better, taller, slower, I don't know what, from another. So you have to do additional analysis, but this is not a problem. This is one observation we are currently struggling even in our journals. If you are looking to explore gender differences, ANOVA is more appropriate, although we are calculating the differences only between two groups, because independent sample state tests assume that participants are randomly assigned to each group. In gender, we know that it's not a random assignment. And non-parametric equivalent test is cross-Calvalis test. So here we were calculating differences within among four groups. So we had results of volleyball players in vertical jumps and some anthropometric features. Here are the groups of volleyball players: opposite, middle, libero, setter, receiver. And here are their results in body height, body mass index. SJ is a squat jump, counter movement jump, block jump. Block jump is volleyball specific jump in volleyball in sport, and attack jump or spike jump. Basically, we had to calculate one test for all differences and then calculate whether any difference between two groups. So you have these small numbers here, symbols here. So for example, in body height, opposite players in the position of opposite are significantly different from libero and significantly different from setter. In body height, they are taller, as you can see, but they are not significantly different than middle players and receivers. So basically, the same approach should be followed in each of these calculations. Here, you have a presentation of all differences, despite the fact I told you previously that in ANOVA, you cannot define the differences between each one of these groups. I'm mentioning it here because actually we calculated one ANOVA, and you have a statistical significance, then you are moving forward to another analysis. It's called post hoc analysis. ANOVA for repeated measures is pretty much similar to t-test for dependent samples, but in this case you will not have, as it was for t-test, two columns, but you will probably have more than two columns, even 3 or 4 columns. For example, I don't know, initial, transitive, and final measurement. In these cases, you will use ANOVA because it will allow you to define the differences for all 3 measurements, and then again you will calculate post hoc. With only 2 time points, you can use a t-test for dependent samples, but if there are more times of measurement, then you have to use ANOVA. ANOVA is required by all means, and not to calculate t-test between these two, t-test between these two, t-test between the, no. Calculate ANOVA for repeated measures because there are some statistical issues you should follow in these cases. So example from the spot, actually I gave you the one. I suppose we have one example from our article. I know that I'm skipping from one topic to another topic in these articles and examples, but this is, as I told you at the very beginning, we will use our examples simply because we are aware what did we do in these articles. And if you have some questions, we can discuss it more objectively. Otherwise, if you will use other people's articles and research, I'm not certain that I will be able to answer your questions. So basically, this is the article where we use analysis of variance for repeated measures. I would like to briefly present you the idea. So we calculated the differences in cortisol, testosterone, alpha amylase, and testosterone to cortisol ratio. You know that these are hormones. Cortisol is a stress hormone, testosterone is anabolic hormone and so on. Alpha amylase is not hormone, but is responsible for metabolism. So pre-match value is a value of cortisol and testosterone and alpha amylase before the match. We actually accepted that the cortisol will increase from pre-match to halftime, and maybe from halftime to the end of the match. This is post-match, this is end of the match. And the same with testosterone, the same with alpha amylase and testosterone to cortisol ratio. As you can see, the differences, significant differences, are evidenced only for testosterone and for alpha amylase. Let's see what's going on. Actually, testosterone increases from pre-match to halftime and from halftime to post-match. I don't know the significance of each difference, but it doesn't mean. And this is especially the case for alpha amylase. As you can see, 99 to 65 at halftime and 408 to post-match. Basically, it shows that something is going on. For the interpretation of the background, you should ask Professor Foretich or Professor Nikolowski, because I don't know anything about it. But still, analysis of variance for repeated measures was pretty good analysis for this purpose. So, let me put some conclusion about this analysis of differences. If differences are found, it means that differences among groups exists. Among groups or among measurements, it doesn't mean. However, we still don't know how big these differences are, or we have, in other words, we have no information on magnitude of such differences. In most cases, journals today ask for the calculation of effect size differences, and the most common used is partial eta squared, or in some cases Cohen's d, depending on the type of analysis used, where you actually present the significance in more understandable wording. So what I'm trying to point that in some cases you will have significant differences, let me put it this way, between two data sets, but because of the large number of subjects. And these differences will be significant, but when you calculate the effect size, you will see that it's not huge. Also, in some cases, it's important to calculate the effect sizes simply because you are dealing with different number of subjects in different subgroups. For example, we had such issue when we calculated differences between starters and non-starters for water polo players playing as perimeters, outer players, and central players. In each water polo team, you have twice more outer players than central players, and it's much easier to achieve statistical significance for outer players, wingers and outer. And because of that, calculation of effect size is very useful because it will allow you to see what's going on in real nature and not only in statistical terms. Second important issue is that in most cases, when you calculate, as I said previously, analysis of variance, you will have results of overall differences among, I don't know, 3 groups. But still, you don't know anything about differences between each pair of groups. So here we have one example of such example, where we calculated jumping and agility in professional basketball players in terms of bilateral symmetry. and we tried to differentiate the performance level and playing positions. We all know that in playing positions, we have basically 3 playing positions in basketball, more than even 5, but in most cases we actually calculate differences between 3 playing positions. So in these cases, you will calculate first analysis of variance, general results, and later on calculate the post-hoc analysis as I presented you previously for volleyball players and their jumping performances. And quickly about analysis of associations, because we don't have much time. So just a moment. Pearson's correlation coefficient, I believe we all know that this coefficient is used to identify associations between 2 different variables. The values are from -1 to +1, where 0 means there is no correlation. 1 means that there is a positive correlation, and -1 means that there is a negative correlation. Most common wording is when you have a positive correlation, if variable A increases, variable B also increases. But the crucial point is increases. It doesn't mean that it improves or not. We are talking about numerical terms. And the negative correlation, if variable A increases, variable B decreases. So here are some correlation diagrams. I believe you will understand it these are very simple. The first one is about 0 correlation, where you have no idea what will happen with the subject if we will increase the value of value x, because there is 0 correlation between these 2 variables. This is maximal positive, this is maximal negatively. Actually, it's impossible in real world, but it looks like that, where you have an assumption that increase of variable x will result with the increase on variable epsilon. And oppositely, this is a negative correlation where the increase on variable x will result in decrease in variable epsilon. There are some most common wording of values, correlation values, meaning that 0.36 to 67 means modest or moderate correlation, 68 to 1 indicates a strong to high correlation, and more than 90 means very high correlation. Basically, in sports science, you can expect these strong correlation as being sufficient from 68 to 1, not to 1, but 68 to 80, let me say so, as expected values in sports science. So for high, for weak, non-parametric example, and finally logistic regression. Logistic regression, I will just briefly mention it, but I strongly suggest you to try to overview this analysis more in details, because there are numerous benefits of using this analysis in sports statistics, in sports science. Although this analysis came from epidemiological sciences mostly, but because of some pros and because of some advantages of this analysis, it's spreading widely in all kind of in all sciences, including sports sciences. We are using it extensively, and because of that, because you can use both quantitative and qualitative data at the same time. So this is a huge advantage in sports science, because in most cases in sports science you will have a situation that some data are organized as quantitative and some other are organized as qualitative. Here is one example, maybe just to cover it quickly. I know that it's not strictly about sports science, but as I told you, health-related sciences are emerging into sports sciences.
where you can use different kinds of data and calculate the odds for something that will occur or not. For example, in sport, you can use it for being very successful or non-successful and so on. So basically, this is it from me. Barbara will now continue. She's here now. I will give her the credentials. Just a moment, make host. Yes. Barbara, you are host now. I will stop recording right